Sinusoidal nature of simple harmonic motion. The position as a function of time for an object in simple harmonic motion can be derived from the following equation: x equals a cosine theta, where a is the amplitude of oscillations. But it really doesn't matter whether it's sine or cosine. If you start your clock when mass is at 0 at the equilibrium point, you would use sine. If you start when it's at the maximum amplitude, you would use cosine. So for our purposes, let's assume that you're looking at the motion of a mass spring system and that you start the clock when the mass is at the positive amplitude. Now we can derive the equation for position as a function of time. So we'll start with x equals a cosine theta. And since omega is theta over t, we can replace theta with omega times t. This is from rotational motion. Omega equals theta over t is similar to velocity equals x over t, and x is equal to v times t, so theta is equal to omega times t. And now we can also replace omega with 2 pi f, or 2 pi over t. That is similar to v equals 2 pi r over t, where a is the amplitude, capital T is period, and lowercase t is time. The graph of position versus time for an object in simple harmonic motion with an amplitude of 2 meters and a period of 5 seconds would look like this. We can see that here the amplitude is 2, and then the period is 5 seconds. So this particular graph would have an equation of x equals 2 cosine 2 pi over 5 times t. We can also derive the equation for velocity as a function of time. V equals negative v naught sine theta. Since v equals omega times r, we can replace v naught with omega times a, as well as theta with omega times t. So we get v equals negative a omega sine omega times t. And again, we can also replace omega with 2 pi f, or 2 pi over t. So we have v equals negative a times 2 pi over t times sine of 2 pi over period times t. And again, a is amplitude, capital T is period, and lowercase t is time. The graph of velocity versus time for an object in simple harmonic motion with an amplitude of 2 meters and a period of 5 seconds would look like this. So we can see here that the period is still 5 seconds. But this amplitude is at the maximum velocity. It is not the amplitude of oscillation. So for this particular equation, we get v equals negative 2 times 2 pi over 5 times the sine of 2 pi over 5 times t. So right here is 4 pi over 5, which is equal to approximately 2.5. And we can see that the amplitude, meaning the maximum velocity, is about 2.5 meters per second. We can also derive the equation for acceleration as a function of time. A equals negative a naught cosine theta. Since a is equal to r times omega squared, we can replace a naught with the amplitude times omega squared, as well as theta with omega times t. A equals negative a omega squared cosine omega t. And again, we can also replace omega with 2 pi f, or 2 pi over t. So we get acceleration equals negative a times 2 pi over t squared times cosine of 2 pi over t times t, where a is amplitude, capital T is period, and lowercase t is time. The graph of acceleration versus time for an object in simple harmonic motion with an amplitude of 2 meters and a period of 5 seconds would look like this. Again, you can see that the period is still 5 seconds. However, this amplitude represents the maximum acceleration, not the amplitude of the displacement. So we can make this equation a equals negative 2 times 2 pi over 5 squared times cosine of 2 pi over 5 times t. Now this part right here would be negative 8 times pi squared over 25. And that is about equal to 3.16. And so you can see on the graph that the maximum acceleration is about 3.16 meters per second squared. Now we can see all of the graphs together. So take note that when the position is at the positive amplitude, the acceleration is negative and the velocity is 0. Or when the velocity is at a maximum, like here or here, the acceleration is 0 and the position is 0. The graphs of kinetic energy and potential energy versus time for an object in simple harmonic motion with an amplitude of 2 meters and a period of 5 seconds would look like this. What things do you notice when you look at these graphs? Well, you should notice that the period is half as much. Here we can see the period is 2.5 when the actual period of oscillations is 5. Also, there are no negative values, and they have the same maximum but at opposite times. So here we have a maximum that's a little over 9, and here we also have a maximum that's a little bit over 9. You should also note that when the kinetic energy is 0, it would be at either the positive or negative amplitude. And when the kinetic energy is at a maximum, this is when it's passing through the equilibrium point. Likewise, when the potential energy is 0, it is passing through the equilibrium point. And when the potential energy is at a maximum, it is either at the positive or negative amplitude. Next, you're going to use this graph to answer following questions. Here it is with a quarter of the period, half of the period, 3/4, and a full period marked off for you.